In the next part, you were tasked with figuring out the K of the spring. Make sure that you click on lab, not on info, vectors, or energy of any sort, just the lab. Then you should have one spring. So what we're going to click is the natural length, unstretched length of the given spring, and we are also going to take advantage of the movable line. So movable line is this red one, and that would be used it's like a little laser pointer that would allow us to kind of clearer see where to measure. And we're also going to use this ruler right here, which is 10 millimeters. All right, so that's 1 centimeter, which is 0.01 meters. The first thing I'm going to start at 50 grams. So I'm going to hang a 50-gram mass on this spring, and I'm going to let it just stop vibrating and be at rest. Then I'm going to take this red line, point it to the tip of that vector which shows displacement, and use a ruler. So using this ruler, lining it just so, shows me that this is I would say almost 0.9. I would not go for a 0.85. That's not 0.85. This is 0.9. And believe me, 9 millimeters is good enough for this lab. So this is 0.9 centimeters, which you have to divide by 100. So this is going to be 0.009 meters for displacement. I'm going to change this to 100. So if this is 100, that's a trick right there. Hang it and just change the mass so you don't have to rehang it. And then there we go, just about like so. This looks like, I would say like 17 millimeters. I will just use that because this is just me demonstrating to you how to do this lab. So I'm going to go back to the data and show you how you should solve this. So draw a free body diagram, and I hope and pray you are pros at this by now. Free body diagram, don't have to be elaborate about the object. It can be just a dot. So this is my weight, and because it has mass, it obviously has force of gravity. Boom, this is force of gravity. See, it even gives you a hint about these two forces. That is all you got there. These two forces are the only forces applied when that is at rest. So you have mg and force of the spring equal to each other. Force of the spring equals force of gravity. The object is at rest, therefore net force equals 0. So that's how we end up with that force of spring equals force of gravity. And that is Newton's first law. An object at rest stays at rest unless there is an unbalanced force applied to it. And all forces here, the two of them, are balanced. They are equal and opposite. Mass I had in grams, but I'm going to go ahead and turn it into kilograms. So one of them was 50 grams. So I'm going to turn this into 0.050 kilograms. And then the other mass was 100 grams. And I'm going to turn that into 0.100 kilograms. Force of the spring, a lot of you went, how do I know that? Look up. You have force of gravity and force of spring equal and opposite. So the value is the same. How do we find force of gravity? Right here. Mass times 9.8. Mass needs to be in kilograms. So if I have 0.05, that's like 5 times 9.8. Remember, we had that as 49. So then if it's 0.05, this is going to be 0.49 newtons. So force of the spring in newtons is going to be 0.49 newtons. And then remember how I measured that, and it was 9 millimeters. So in meters, that's going to be 9 divided by 1,000. So that is 0.009 meters. And then K from here is going to be 0.49 divided by 0.009. You get your calculator and calculate what that is. The next one was 100 grams. That's going to be 0.1 times 9.8. It's going to be 0.98 newtons. And then I believe I said it was 1.7 centimeters. So that is 0.017 meters. And then I take the 0.98 and divide it by 0.017. That's going to be newtons per meters. Then grab your calc. So for the first one, I got 54 newtons per meter. So that's going to be 58 newtons per meter. And then the next one is going to be something different. Take another 2 measurements and then average your total. And then the second spring needs to be set to a 6. So I set it for the second spring. See how I moved this to 6? 1, 2, 3, 4, 5, 6. And that 50-gram hanging gets me 0.6 centimeters. So that's going to be 0.006. 2 zeros and then 6. And then if I make it 100 grams, that becomes, once it gets to rest, I read 0.11 and a half-ish. Yeah. 50 grams and 100 grams, the forces are still the same. Then our distances are now 6 millimeters and 11.5 millimeters, 0.0060 and 0.0115. And then that gets me 82 newtons per meter and 85 newtons per meter. And you can collect the other two and average your overall. And then I will do the next video for the practice problems.